Chapter 4 Nature of Waves 4.1 Wave Motion. Let's begin. Communication between elephants. Many animals communicate by sound and vision. Elephants communicate even by vibrations as they rumble, which travels through the ground to much further away. 1. Waves and vibrations. Oscillations or vibration produces waves. There are water waves, sound waves, and microwaves, which actually belongs to electromagnetic waves. Well, stadium wave is also the kind of wave. Have you taken part in a stadium wave? How does it work? 2. Waves, energy, and matter. Most waves in daily life are traveling waves. In the following experiment, the ping-pong ball is set into vibration by the disturbance produced by the water wave. In the experiment, the wave transmits energy from one end of the tank to another, and that also explains how the ping-pong ball gains kinetic energy. However, the ball does not actually move outwards with the wave, and we conclude that the wave transmits energy, but not matter. 3. Transverse and longitudinal waves. The following experiment shows the vibration and traveling of transverse wave.
We will use this slinky spring to study the properties of transverse waves. Attach a ribbon to the middle of the spring as a marker. Lie the spring on the floor and stretch it. Flick one end of the spring sideways to send a transverse pulse across the spring. Observe the motions of the pulse and the ribbon. How do the pulse and the ribbon move? If we stretch the spring more to increase its tension, how does the speed of the pulse change? Now, flick the end of the spring continuously to produce a transverse wave. Observe the motions of the wave and the ribbon. How do the wave and the ribbon move?
So, for the transverse wave, the direction of vibration of particle is perpendicular to the direction of propagation of the wave. All particles just vibrate about their respective original positions and never actually move away. A transverse wave consists of a series of crests and troughs. And as the wave travels, every single particle will form a crest and trough in turns. Using the same slinky spring, the following experiment shows the vibration and traveling of longitudinal waves.
Lie a slinky spring on the floor and stretch it. A ribbon is attached to the middle of the spring as a marker. Give a sharp and sudden push to one end of the spring to send a longitudinal pulse across the spring. Observe the motions of the pulse and the ribbon. How do the pulse and the ribbon move? Next, give a sharp and sudden pull to the spring. How do the pulse and ribbon move? Now, push and pull one end of the spring continuously to produce a longitudinal wave. Observe the motions of the wave and the ribbon. How do the wave and the ribbon move?
So, for longitudinal waves, the direction of vibration of particle is parallel to the direction of propagation of the wave. All particles just vibrate about their respective original positions and never actually move away. A longitudinal wave consists of a series of compressions and rarefactions. And as the wave travels, every particle will form a compression and a rarefaction in turns. In general, all waves can be classified into transverse wave and longitudinal wave. The vibrations due to an earthquake is a combination of longitudinal wave and transverse wave. Spend a few minutes on the section below to learn some basics about earthquake. Do check point 1 on the next page.